Welcome back, digital seekers. In the last episode of graph databases, we have seen what is the origin of graph databases, how databases have evolved over a period of time. So in today's session, let us talk about the more in detail about graph databases, what are the different flavors of graph databases available, and which one to choose from based upon your use case. So stay tuned. First of all, what is a graph database? A graph database is a database wherein you actually use nodes, edges and properties instead of columns and tables for storing and retrieving data. Before we get into the graph database, there is a word Semantic Web coined by Tim Berners-Lee, who is the inventor of World Wide Web. What he says is Semantic Web is a web of nodes which can be processed directly or indirectly by machines. So this is a coined word from Tim Berners-Lee, and soon after that there were a rush of ideas, and the first one to surface is resource description frameworks, RDF stores. So over a period of time there are property graphs also which came into picture. So first let us talk about RDF stores. So when you see RDF stores, they actually store and retrieve the data in the form of subject, predicate, object. So that means there are three entities, three elements: subject, predicate, object. So here predicate represents a relation, subject represents the subject, the vertex, and object is also a vertex or a letter. So there is a very big vocabulary when it comes to RDF stores. So we will discuss that in a bit. RDF stores are primarily used for storing and retrieving knowledge graphs. So when you have a lot of information which is highly connected and it is a dense graph, it can be represented by using a knowledge graph. So as we have seen, the knowledge graphs or RDF stores are actually maintained as subject, predicate, object. So it is a triple, so which can also be called as a turtle, and they also have quads to represent RDF stores. Quads is actually a fourth dimension added to the triples, which is primarily used for named graphs. So we will talk about it later. So when it comes to RDF, there is a lot of vocabulary like resources, classes, labels, properties. We will see the entire vocabulary in the next slide. Traversing this knowledge represented in the form of RDF stores is done by using SparkQL, which is similar to your SQL structured query language and which is primarily used for querying the RDF triples. Knowledge graphs are a W3C recommendation for information exchange, and also this is a key technology for semantic web. RDF stores the data in the form of subject, predicate, object, as we have already seen. So here subject and object are actually vertices. So they can be represented by a unified resource indicator, URIs, or it can as well be a literal value. And whereas in case of edges are again URIs. So it becomes our responsibility to come with a unique URIs for edges, vertices, so that they can be represented well in a knowledge graph and they can be used in queries for retrieving the data. Whereas if we go into property graphs, so property graphs are represented by using only three elements: vertices, edges and properties. So vertex and edge both have unique IDs and they have key value pairs which are properties. So every vertex and edge can have any number of properties, there is no limit on that. Property graph databases are traversed by using Gremlin, or you can use any proprietary query languages like Cypher in case of Neo4j. When we go back to RDF and then see the entire vocabulary of RDF, so the entire vocabulary of RDF is so big that it is going to take quite a while for somebody to get their head around and then understand all the available vocabulary and then define a schema and then use it. So it is not so straightforward. As you can see, there are so many elements out there that you have to understand in depth before you can actually model your knowledge graph and then use it. There is one more definition from Tim Berners-Lee. So he says semantic web is not artificial intelligence. At this point in time you might be wondering, so is semantic web an artificial intelligence because we are talking about machines understanding data? No. So Tim Berners-Lee says no, semantic web is not artificial intelligence. Semantic web, in case of semantic web, what he says, it is the responsibility of the human beings to clearly delineate the data, clearly define the data in a well structured way so that a machine can understand and reason about. So it is not the machine's responsibility, it is the human's responsibility when they are storing the data, right? So you can actually find what RDF not in the given URL there. So it will give you a clear description of what all Semantic Web is not aiming at delivering, right? So far we have understood what is RDF, what is property graph database, and what is RDF not. So now let us try to understand what are the use cases they are set out to solve. So let us first consider RDF stores. RDF stores, we have already discussed that they are actually used for storing and retrieving knowledge graphs. So now let us say you are a news aggregator. So what you will be interested in, you will be interested in getting the data from multiple news channels, aggregate the information, compare and contrast between the similar articles, and provide your own analysis on top of that. Now to do that, you need a standardization across the news agencies to publish the data in the similar format. Let us say knowledge graphs or RDF stores are going to be used by all these news agencies. But what is the guarantee that they are all going to use it in the same way? To arrive at that guarantee, we have schema.org, wherein they have clearly defined how a person need to be represented, how an industry need to be represented, how a business need to be represented, how a news article need to be represented. They have actually come up with very vast list of such classes, definitions. So now everybody following the similar standards, they can actually publish the data and you can consume that information and you can aggregate, you can analyze, and you can provide your own analysis on top of the aggregated information. So that means for publishing and consuming this information, RDF stores are very valuable resource. And SEO, search engine optimization. Why? Because Google advocates all of us to use schema.org and then their classes for defining rich snippets and rich cards so that Google can understand what we are talking about, what is the content of that web page. So we have to define it using a schema.org template, and Google will crawl through that information and store it in a knowledge graph and retrieve it whenever the user is searching for that information. So here for SEO, Google is actually using knowledge graphs. And data integration and reasoning. So data integration is primarily, as I said, when you are actually looking for information exchange from one database to the another database format, like say you wanted to exchange the information from a relational database to a property graph database, from a relational database to a NoSQL database, or from a NoSQL database to a relational database in any format. So you can actually use RDF as an intermediary. You can actually use RDF as an information exchange format. That means you will first convert anything into RDF, and then from RDF you will convert into the other database. Why? Because RDF is structured. So it is clearly defined and very structured. So you can easily transform that structured information into either an unstructured information or another structured form of information. Now, let us see the same thing with respect to the property graph databases, what they are set out to solve. Property graph databases actually gives you AECAD, atomicity, eventual consistency, isolation, and durability. So any use case that you have which can be solved by a relational database can as well be a candidate for property graph databases. So property graph databases can be used for solving any relational use case that you have at hand. And they actually provide you high throughput transactions and truly distributed databases. They actually support even social scale applications. Now let us take a use case and try to see how the data is represented in the form of RDF stores, and the same data how we will represent in the form of a property graph database. For example, let us see the example that is given on the RDF side. So we are talking about the English statements which we need to represent in RDF store. The same statements we are going to represent in the form of a property graph database. So let us see the English statements first. Dog 1 is an animal, cat 1 is a cat, cats are animals, zoo hosts animals, zoo 1 hosts cat 2. Now to represent this data, we actually have the graph represented there. EX dog 1 is of type animal, and then cat is subclass of animal, and we are saying cat 1 is of type cat. Again, cat 2 should be of type cat, and zoo 1 which hosts cat 2, and zoo hosts animals. To represent this information in case of an RDF store, we need to have so many number of triples, like dog 1 type animal, cat 1 type cat, cat subclass of animal, host range animals, zoo1 host cat2. So to represent this data in a schematic way in the form of RDF store, it might be at least a bit easy to understand, whereas when it comes to the actual notation of the data, so it is all triples that you will actually store in the database. Now let us try to see the same data structure, same data representing in property graph database. In case of a property graph database, you don't necessarily need to have a class separately and then map the entities with the class. Why? Because it is labeled property graph. So you have to remember these are all labeled property graphs. That means each vertex and each edge is also labeled. So when you say animal, type cat, name cat1. Animal, type dog, name dog1. So animal type cat, name dog, name cat2, and zoo, name zoom1, host cat2. So representing this information, this very same information in case of a property graph database is going to be quite simpler. Why? Because edges and vertices both can have properties. Now this is not going to be very evident with this simple use case. Let us now get into a more complex use case and try to understand how RDF is going to represent the data and how the same data can be represented in a property graph database. Here we have to understand one thing. So when we are representing RDF stores, you need to have a very clearly defined schema. So for defining a clear schema, you need to have a meta schema which is going to define the elements that are going to be defined in a schema. So it is very much necessary. Why? Because your data need to be processed by machines. Remember? So we are building knowledge graphs to be processed by machines. So how we will ensure that? We'll actually define a meta schema first. So in the meta schema, on the very top of the screen, you can actually see that there is a literal which is represented by rectangle, and there is a resource represented by curved rectangle, and a class defined by a novel, and a property represented by small circle. Now with this notation, you can understand how you are going to define your schema. So within the schema, you can actually see that there are all vowels. That means they are all classes. So now how you will understand the schema? The first one is artist creates artifact. So now creates is a predicate. So for a predicate, there is always a domain and there is a range. Domain is the place where the relation is originating from. Range is the place where the relation is going to. So let us see the creates. So creates has a domain artist and creates has a range artifact. That means an artist creates artifact. This is how you read it. Artist creates artifact. Similarly, sculpture sculpts sculpture. Painter paints painting. Now, sculpture and painter are subclasses of artist. Similarly, paints and sculpts. So these are subclasses of creates. And sculpture and painting are subclasses of artifact. And painting is also a subclass of a commercial good. That means the same class can be a subclass of multiple classes, multiple inheritance, right? So now, once you represented this, there are properties. So you can see the small circles there. First, last, title. These three are the properties. First and last have the domain as artist and range as a literal. That means they are not going towards a class, they are actually going to represent a value, literal value. That is the reason why they are properties. Similarly, title has a domain, artifact, and title has a range, literal, right? So that means even title is going to be a value which is going to have a domain, artifact. So now you understood what are the domains, what are the ranges, what are classes, and how the schema is represented. So to recap, artist creates artifact with a title. Artist has a first and last name. And sculpture, who is of type artist, who is a subclass of artist, sculpts sculpture. Sculpture is again a subclass of artifact. Painter, which is a subclass of artist, paints a painting. Painting is again a subclass of artifact. which can as well be sold, which is a commercial good, right? So now let us try to create instances of this class and represent the data, because our aim is not to create a schema. Our aim is actually to create a knowledge graph. Knowledge, that means we have to create the knowledge. So how you will do that? So that is defined in the bottom section. So instances. So what you are doing, you are actually creating an instance of sculpture. So sculpture R4 is actually of type sculpture, and it has a first and last names, which is Auguste Rodin. And his R4 sculpts R5. R5 has title The Thinker. Similarly, R1 has a first Pablo and last as Picasso, and R1 paints R2 with a specific title. R1 paints R3 with a specific title. So here what we are seeing is everything is represented as triples. So how you will understand which are the triples? So every arrow has a domain and range. R4 is the domain for first and Auguste is the range for first. That means R4 first Auguste, R4 last Rodin. This is how you define your subject, predicate, object, right? R4 sculpts R5, R5 title The Thinker. So you will have so many triples to represent the knowledge information, saying that Auguste Rodin sculpts The Thinker. 4 triples to represent Auguste Rodin sculpts The Thinker. Similarly, Pablo Picasso, R1 paints R2. Pablo Picasso, R1 paints R3. So we are representing the knowledge now, right? So far we have used very limited vocabulary from the entire RDF vocabulary list. So you can see the entire vocabulary on the right side. So now let us try to represent same data with enhanced information in a property graph. So you can now see that everything is coming as rectangular boxes. Each box has name value pairs, they are the properties, and each box has a label. So the dotted boxes are edges and the solid boxes are vertices. This is our notation now. So artist R1 with first name Pablo, last name Picasso, who is of type artist, who is actually painted painting R2 on 15th June 1834. Similarly, he painted R3 on 15th August 1784. And similarly, we have a sculpture who is Auguste Rodin, who sculpted on 12th July 1834 sculpture The Thinker R6. So now we have represented all that information in very few vertices and edges. So using very few vertices and edges, we have represented all that information, and also we enhanced it with an additional information on which date that has happened. On top of that, you can actually add one more link between Picasso, Pablo and Auguste Rodin, saying that they are friends. They are friends since a specific date. Okay, so this is how you represent complex data in form of a property graph database. So representing the same information in RDF stores requires more triples. Why? Because you cannot have properties on top of edges. So what you would end up doing, even the edge you will be modeling as a vertex. So now edge is modeled as a vertex, so you have additional triples to come, right? Now let us see the differences between RDF stores and property graph databases. In RDF stores, no two connections have the same edge. That means the same edge cannot be repeated between two nodes multiple times. That means Raju likes Priya in his childhood, Raju likes Priya in his teenage, Raju likes Priya even now. So similarly, Raju likes a specific movie in his childhood, he likes the movie in his teenage, even now. You read a book in your childhood and you liked it. Read is one edge, and then you read the same book in your teenage, you read the same book now. So here the reading has happened multiple times. So you cannot represent the reading part multiple times in between these two vertices in RDF stores, whereas it is possible in property graphs. You can still have some workarounds in RDF stores, and then you can still go ahead and then implement multiple links of the same name, but it is actually going to make it more complicated, adds more triples to your graph store. your RDF triple store. Okay. So in RDF, there are no attributes and relations. We have already talked about it. RDF uses quads for named graphs. So when you have named graphs, so when you want to represent more domain knowledge, that means if you want to actually specify the domain wherein that knowledge need to be maintained, so that is where you actually create a named graph. So the name is represented as a domain. So now that domain gets duplicated across all the triples for the domain. So which is a duplicity, but at the same time it is going to give you more clarity which domain, which triples are meaningful, right? So similarly, there are even property graphs wherein you can actually have named property graphs. So they are also there. And they are there only in a few cases, not in all property graph databases they support named graphs. Okay. So RDF uses, quads, we have already seen. So RDF uses more triples for the same data that need to be represented in a property graph. So we have already seen that every information that is represented in a property graph requires a triple, one or more triples in case of an RDF store. Why? Because if you are trying to represent a property for an edge, so that is more triples in case of an RDF store. So now the question that will come to your mind is when to use a graph database, right? So we have to first understand the definition which the graph databases are set out to solve. So graph databases set out to solve retrieving related information reliably and efficiently at scale, say petabytes and exabytes. I'll ask you to answer these questions, and if you have answered at least 4 questions yes, that means you are looking for a graph database. So the first question is, do I really need social scale applications, and can I forego ACID in place of AECID? So is that a viable choice for me? So if I am using relational database at the moment. So do I have or can I develop a graph skilled team? So because graph is a new skill that you are going to bring into the table, so can you build a graph skill team, or do you already have a graph skill team is a question that you have to answer. Is my application going to have complex join queries? If you are already using relational databases and you have tons of tables all related, and then you are querying the data for retrieving it, and then you are joining lot of tables for retrieving information, and your queries are actually working pathetically slow. So this is where the relational database really sucks, when you have a lot of tables and then you have to join so many tables for retrieving information. This is where relational database has a big limitation, and this is easily solved by graph databases. And do I need high throughput transactions? So you have, as I said, you have tons of tables, and then your transactions are taking a lot of time because of your triggers that are getting fired whenever you are inserting data. So you have a lot of things happening behind the scenes apart from your insert queries or your update queries. So now you have to really think about, do I need to have transactions which are real time? Okay, so these are the cases wherein you have to actually go for a graph databases. So now if you have answered any 4 of these questions yes, then it is certain that you are actually looking for a graph database. Now let us see which database to choose from. Again, in graph databases there are so many different variations, so many varieties of graph databases available. You have to pick the right one for your need. In my career I have worked on different graph databases, starting from Titan, OrientDB, DataStax Enterprise Graph, Neo4j, and then Janus Graph. So I'll fairly give you an idea about choosing one of these graph databases. So you can choose something similar with capabilities based upon capability matrix. You can choose the right database for your need and your skill. So if you have a graph team which is capable of doing an ArangoDB, then go for it. The first question that you have to ask yourself is, am I building a graph database for machines to understand or humans to reason about? If it is machines to understand, no question, you have to go for RDF stores, because RDF stores are meant for knowledge graphs and they are easy to reason about by machines, right? And there are many RDF stores again. I'm not classifying them. Why? Because right now I don't have enough expertise to talk about RDF stores. But if you need more information about RDF stores, I can always fetch that information for you. You can comment down below, right? And if you are looking for humans to relate and then reason about your database, then you are looking for a property graph database. So now within property graph database, are you looking for an enterprise support? So there might be use cases wherein you might need an enterprise support. Why? Because your application is very critical, and then you cannot really wait for the community to help you out, right? So in those cases, you might need an enterprise support. So then you can actually go for the enterprise supported databases. So there again you have another choice to make. Do I need truly distributed database, or a single node is going to be sufficient? So truly distributed means your data is distributed across data centers. Let us say you have a data center in India, data center in US, data center in Europe, and then you have data which is concentrated within India is maintained in India data center, and then all these three data centers have different data sets, and they're all related and forming one single unit database. So this is truly distributed database. So if you need such a truly distributed database, then you have to go for DataStax Enterprise Graph. And whereas if a single node is going to be sufficient and multi-node master replication is also going to work out for you, that means every node is going to have the entire data. So if it is going to work out for you, then you can actually go for Neo4j or Azure Cosmos DB. If you ask, can I not use DataStax Enterprise Graph for a single node? No, you can definitely use DataStax Enterprise Graph even for a single node. So it is a choice for you to make. If you want a distributed graph database, you have to go for DataStax Enterprise Graph. When you want to use single node cluster, you can go for DataStax, Neo4j or Azure Cosmos DB. So Neo4j has recently started experimenting with distributed databases. So it is far from reality right now at this point in time. So this is about when you need enterprise support. If you have opted for open source database just because you don't have enough funding, or you are more interested in open source and then you want to contribute, you want to learn, and then you want to enhance that product, then yes, very well, now again you have option to make whether you want truly distributed database or you want single node cluster. So if you want a truly distributed database, you better go for JanusGraph, and which is a descendant of Titan. Or if you want to have a single node cluster, you can definitely use JanusGraph. You can use Neo4j community version. You can have OrientDB. So you have various options when it comes to open source as well as enterprise supported versions. Now what you see on the screen is actually the graph database engine rankings. So these engine rankings are actually based upon popularity rather than capability. So popularity is going to be directly proportional to capability and also the time of arrival into the market. So at one point in time in 2015 is when I started using Titan. So Titan is in the second position competing with Neo4j. Of course, Neo4j is far apart. Why? Because it was pioneer when it comes to the property graph databases, and Titan used to be in the second place. And that is when I evaluated Titan and Neo4j for one of our clients, and then we opted Neo4j because we wanted enterprise support. Now let us briefly look at the history of property graph databases, how they have evolved over a period of time. So in the year 2010 February is when Neo4j 1.0 was released into the market. That was a big hit at that time. And in the year 2011, Marco Rodriguez met Matthias Brocher, and then the idea of Titan actually has begun, and then it started shaping up. So in the year 2014 August is when 0.5 version of Titan has been released. And it has immediately gathered a lot of attention from the community. Most people started adopting it, and by December 2014 Titan 0.9 was released, and that is the time when I started using Titan and evaluating it for a couple of our products. And in January 2015 Apache Tinkerpop, which is actually a graph standardization, which is with the aim of standardizing graph databases across the across the table, has entered Apache incubation. And in February 2015 is when DataStax has acquired Aurelius, which is the parent company of Titan, and the entire community which is using Titan for their graph needs has been in a dismay. They were just wondering whether they have to continue using Titan or whether they have to drop, because there is no taker in the market for Titan. So in the year 2017 January, JanusGraph was released under the hood Linux Foundation. So Linux Foundation has adopted Titan 1.0, and they have released JanusGraph in the year 2017 January. So 2017 June, DataStax has released their first commercial version of DataStax Enterprise Graph. So this is the history of graph databases, property graph databases, and my touch points wherein I have used these property graph databases. And we are using JanusGraph for all of our products. And we have been very satisfied with the kind of releases we are seeing from JanusGraph, and the continuous support that we are seeing from Linux Foundation for JanusGraph. We are very happy with that. And now with this I want to conclude this session, and if you have any questions, whether it is related to RDF stores or property graph databases, please comment down below. I am very eager and happy to help you out. And though I haven't worked much on RDF stores, I have briefly worked on it, and then I do know about the semantic web, and then I have used it for a couple of use cases. But I cannot classify myself as an expert there, but I can definitely drill information and then help you out to understand more if you wanted to know more about RDF stores. And going forward, all the sessions that I'm going to take in graph databases are going to be property graph databases, unless otherwise somebody is asking for RDF stores. So, and I'm going to put the list of upcoming sessions on the slide, so you can actually go through that. And thank you very much for staying with me so far, and happy time learning, fun time learning graph databases. Stay tuned, stay focused, and be safe. Thank you very much. Have a nice time. Bye bye.